Hello and welcome back, business calculus students. And here in this lesson we're going to be working on some vocabulary and some background that we need to know. Specifically, what does it mean when we say a function is continuous? And what is a discontinuity? So taking a look at example 1, it asks us, draw the function f of x equals x squared in the xy plane. And so we'll use this xy plane. If I let x be 0, well then 0 squared is 0, I have a dot right here. If I let x be 1, then 1 squared is 1, I have a dot right here. If I let x squared be, well, if I let x be 2, then x squared is 4, and so on. This is an even function because it has an even exponent as the exponent in this power function. So maybe you remember that from algebra. But basically what that means is I should have symmetry across the y-axis. And if you try it out, -1 squared is 1, -2 squared is 4. So you maybe see where this is coming from. But what I'm trying to do right now is just drawing this function. And maybe you're familiar with the shape of this function if you've taken algebra classes before. This is what we call a parabola. And it's a little bit difficult for me to draw on this program, but this is the parabola that represents y equals x squared. This is the curve that represents this function here. And down below, it says, example 2, draw the function g of x is equal to x divided by absolute value x in the xy plane. We'll use this plane over here. So here's my x-axis, my y-axis. And let's evaluate what would this be if x were equal to 1, right? Well, if x is equal to 1, this would be 1 divided by absolute value of 1, so it would be 1. If x were equal to 2, my function would be 2 divided by absolute value 2, or 2 divided by 2, that's also 1. What you can find is that for any of the positive values of x, my function g of x down here is always going to just be positive 1. But if we take a negative value of x, like if we let x be -1, g, my function g right here, evaluated at -1, will become -1 over absolute value -1, which would be -1 over 1, which would be -1. So when x is equal to -1, the value of my function is -1. And what you can find is that using this function right here, g of x, anytime you plug in a negative value of x, the output of the function returns the value -1. And that's true for all negative values that we could have for x. And this positive one is the output of the function for any positive value we could choose for x. Now what happens when x equals 0? Well, here if x equals 0, I have 0 divided by absolute value 0, or 0 divided by 0. But 0 divided by 0 is not a real number. That doesn't map to anywhere along my y-axis. And so to represent this, a lot of times we use a hollow circle when we're drawing a function. And that's just to represent that, hey, for the specific value of x equals 0, my function doesn't map anywhere. It doesn't have an output for the input x equals 0. So here are two examples of just drawing functions. And I want to point out one big difference between these two. And the idea is called continuity. So we say a function is continuous over some interval if, and only if, that function can be drawn in an xy plane without lifting your pen. So let's ask is my first example continuous? Well, yeah, you could actually draw this parabola without ever lifting your pen, right? And we could ask ourselves, what about this red function on the right? Is this continuous? And the answer would be no, this function is not continuous because I can't draw the whole function on the right without lifting my pen. In fact, as I'm going along, drawing from left to right, I actually have to pick up my pen at the y-axis and drop it down again up here at +1. But there's what we would call a discontinuity there, a place where my function is not continuous. Now, these discontinuities come in 4 different flavors. The first flavor of discontinuity is what I would call a point discontinuity, and these are also called removable discontinuities if you're looking at some other textbook. But what I like to call them is I like to call them point discontinuities. Now let's consider the following function. F of x is equal to x squared plus 4x plus 3 over x plus 3. This is what we would call a rational function. And it's a rational function because you see the word ratio. This function is a ratio of 2 polynomials. So in the numerator we have a quadratic polynomial, and in the denominator we have a linear polynomial. So it makes it a rational function. Since the numerator is a quadratic polynomial, we can factor the numerator like this. And so once we factor the numerator, we have that, which is the equivalent form. I mean, it's a different form, but it's equivalent to the function above here. If maybe you remember this from algebra class. I hope you do, but if not, that's okay. Whenever we graph rational functions, if we see that we have the same factor happening in the numerator and denominator, we know that it's going to lead to a point discontinuity. The reason is if we plug in x equals -3 into this function up here, the denominator becomes 0, because if you look at this denominator, x plus 3, well, plug in this here, oops, the denominator would be -3 plus 3, and of course -3 plus 3 is 0. So again, let me just write this out. If I evaluate f of -3, I have something going on up here for my numerator, but my denominator becomes -3 plus 3. So my denominator becomes 0. And we can't divide by 0, and so the function is actually undefined here. Now, aside from this one spot where my function is undefined, here at x equals -3, the rest of the function behaves like f of x equals x plus 1, which is a line. And the reason we know that is because, again, scrolling up to this factored form, if I have x plus 3 as a factor in the numerator and x plus 3 as the factor in the denominator, these two factors cancel. And I'm left with f of x equals x plus 1. But it's important to remember that I actually have a point discontinuity here because I can't allow my denominator to be 0. So I drew a hollow circle again to indicate the location of a point discontinuity, or again, sometimes we call it a removable discontinuity, depending on what book you're reading. These mean the same thing. The second flavor of discontinuity that you might have is called a jump discontinuity. So now let's look at this function. F of x equals x plus 1 divided by absolute value x plus 1. And what I want you to notice is that if you plug in x equals -1 into this function, that would make the denominator 0, wouldn't it? Because I would have absolute value of -1 plus 1 in the denominator, which is absolute value of 0, which is 0. Now, because we can't divide by 0, we would say that the function is undefined when x is equal to -1. So here, when x is -1, I'm drawing two hollow circles here, just to demonstrate that my function doesn't actually take on any real value when x is equal to -1. Now this is different from the point discontinuity because here, in this example, we see that the function jumps in value at the discontinuity. So notice the jump happens because we're hopping along here at -1 in my y value, or the function output value. And then, right there at the discontinuity, we jump up to y equals +1. And so this is the jump in jump discontinuity. Whereas with the point discontinuity, my graph is only discontinuous at a point. Here, it's discontinuous at a jump. So these are the first two flavors of discontinuity. The third flavor of discontinuity is an essential discontinuity, which is also called an infinite discontinuity. And for this, let's consider the following function. This is again a rational function because it's a ratio of a linear polynomial in the numerator to a linear polynomial in the denominator. And think again, if we use x equals -2 and we evaluate my function at -2, this gives me, well, -2 plus 3 in the numerator, and -2 plus 2 in the denominator, which would be 1 over 0. Of course, 1 over 0, that doesn't give me a real number, so it's undefined here whenever my x value of my function is -2. Now, this is not a point discontinuity, and maybe it kind of looks like a jump discontinuity, but the difference here is that on the left side, my function branch is going all the way down towards -infinity. And then across the discontinuity, it jumps all the way up to +infinity on the right side. And so this is a little bit more substantial than a jump discontinuity like before. If you were to approach the discontinuity along this curve from the right side traveling to the left, so, you imagine yourself, you exist here on the right side of the discontinuity, and you start to travel to the left, you're actually going to follow the curve up to +infinity. But if you were to approach from the left side, going to the right, you'd be following this curve down towards -infinity. This is what we call an essential discontinuity, or sometimes we call it an infinite discontinuity because on either side of the discontinuity, we're approaching an infinity, either +infinity on the right side or -infinity on the left side. Okay, now our last type of discontinuity, you don't actually have to worry too much about this, but I do want to mention it. It's called an oscillating discontinuity. And if you consider this function, which is the sine function, it's a trigonometric function, and just as a side note here, in calculus for business and social sciences, we're not actually going to use trig functions in our homework or tests. So you can mostly ignore this example of oscillating discontinuities, but I just want to mention it for completeness. The idea is if you have sine of 20 divided by x, this is what the graph would look like. I actually graphed this using a tool that I encourage you guys to check out called desmos.com. And they have a graphing calculator that's very, very easy to use and probably very helpful if you're doing your homework. But what's happening here is that as you go farther away from the origin, like out here, the waves of my sine function are getting longer and longer, a little bit more flat, if you will. And that happens on either side. These waves are actually are very gentle rolling waves out to the far left or far right. But as we approach the origin, you'll notice that the frequency of oscillation is increasing. And that happens whether we're approaching from the left side or the right side. The frequency tends to be increasing here as we're going towards the origin. Now, the trick here that makes this a different discontinuity than the others, first, let me show you that it's a discontinuity, because if we assume x is 0, if we're concerned about what happens here at the origin, or x equals 0, then we have in here sine of 20 divided by 0, but we can't divide by 0, and we can't take the sine function evaluated at 20 over 0 either. So this is a discontinuity where our function is not defined. But what would we say, what would we say we're actually approaching as, we approach x equals 0? What's my function approaching? It's not really going up to positive infinity or down to negative infinity. And, we're not actually approaching any specific number, because if you were to take any little interval around the point x equals 0, so this is the point, let's say x equals 0, any tiny little interval here, no matter how small you choose it, right? If we let the width of this interval be a very, very tiny number, we let this be a very skinny interval, we're always going to have infinitely many oscillations of our sine wave. Again, no matter how small of an interval you choose around x equals 0, we have infinitely many oscillations of the sine wave. So this is a truly weird function, and it gives rise to a weird type of discontinuity, which we call an oscillating discontinuity. So we can just maybe recap this. With another definition of continuity, we might say a function is continuous over some interval if that function is defined everywhere, so we don't have any places where it's undefined, and does not contain any discontinuities, right? And maybe that's a little bit, obvious or a little bit trite to say that a function is continuous if it does not contain any discontinuities. But if you familiarize yourself with those 4 flavors of discontinuity, that is a point discontinuity, a jump discontinuity, a essential discontinuity, and an oscillating discontinuity, as long as you don't see those happen in your function, you could say you have a continuous function. And, this is the same thing, I want you to realize, this is the same thing as actually saying a function is continuous if you could draw that function in an xy plane without lifting your pen. So they mean the same thing. A few more things, but we're getting close to the end here. Polynomials are always continuous. So remember, a polynomial function, I'll use p of x to represent a polynomial function, always has this form here. We have some coefficient, or some constant term, plus some coefficient times x to the first power, plus some coefficient times x to the second power, or we say x squared, plus some coefficient times x cubed, plus some coefficient times x to the 4th power, plus some coefficient times x to the 5th power, and on, as many terms as you like. This is called a polynomial if all of the powers of x, if all of the powers of x are natural numbers. So as long as these guys, x squared, x cubed, x to the 4th, x to the 5th, if these are natural numbers, then we're talking about a polynomial. By the way, a natural number is a number that belongs to the set 1, 2, 3, 4, 5, and so on. And x by itself is like having x to the 1st power, and notice this constant is also allowed in a polynomial. So one example of a polynomial, maybe to make this a little bit more real life for you, I'll call it q of x. My q of x polynomial could be something like 3x squared minus x plus 17, because I'm allowed to have natural number powers of x, and I'm allowed to have a constant term. So these are polynomials, right? Just a refresher. Now, polynomials are always continuous. They're always continuous everywhere. So this will not have any discontinuities. Now, rational functions, which we talked about before, a rational function, I'll use capital A of x for a rational function, is just one polynomial divided by another polynomial. So like maybe an example of a rational function could be something like x squared minus 7, which is a quadratic polynomial, divided by x cubed plus x to the 5th, right? So I have a polynomial in my numerator, I have a polynomial in my denominator, and the ratio of these two polynomials makes a rational function, which I named b, capital B of x. Now, rational functions can only have either point discontinuities or essential discontinuities. They can have both, but what they can't have, they cannot have a jump discontinuity and they can't have an oscillating discontinuity. And furthermore, rational functions can only have a discontinuity where the denominator becomes 0. So the zeros of your denominator of a rational function, those are where your point discontinuities or essential discontinuities are. But for a rational function, you only have to worry about discontinuities when the denominator is 0, and you don't ever have to worry about a jump discontinuity. All right. Thanks, and I'll see you in the next lesson video.